So any questions from you guys about
No.
No.
okay, so semua orang faham you have to cite if it's not your own Alright, that's good. Okay, kita move on to our chapter 4. Chapter 4. Okay, so we are going to do a little recap on what we have learned. Okay. So saya dah start recording kan? Okay. So we talked about work done and I told you work done is actually the dot product of a force vector with its displacement vector. Both are vectors, however, when we expand this product, it becomes F cosine theta delta x, and this guy is a scalar quantity, which means that it is not a vector, which means that it does not have any angles or direction. Yang hanya the work done only has a positive or negative sign indicating whether the force is in the same direction as displacement. Okay, so you get a positive work done. Or if your F is not in the same direction as displacement, so you would get a negative work done. So this is what the negative and positive sign tells you. It does not give you like direction up, down ke left, right ke tak. Dia akan bagi tahu whether the F is in the same direction as X or if it is not in the same direction as X. So if it tells us whether it is in the same direction as X or not, why is it still not a vector? Now remember that we talked about the dot product of these two guys, and when we expand it, we have this cosine theta component, right? So your F and X can be located anywhere. And I just need to know what is the angle between them. I just need to know the angle between them. So for example, F is this way and X is this way. So the angle between them is 180 degrees. So what if F is over here and X is over here? 90 degrees. F and delta X. I just want to know what is the angle between the two vectors. I don't care if the displacement is not in the X-axis. So sebenarnya kita tak tahu pun direction. We weren't given the direction of delta X as part of the X-axis. Faham tak? So contohnya, let's say we go with this second one. Okay, I say I want to know what is the dot product. Sorry, I want to know what is the work done by these two force and displacement vector. So work done is F cosine theta because I need to find a component that is parallel to the displacement. So I get F cosine theta. I will need to know what is the force, what is the component of force that is parallel to the displacement. So this becomes F cosine theta and then darab dengan delta X. Now I still don't know what the direction of X is. I just know that work done is the F component that is parallel with displacement X. But actually I don't know what is the direction of these two guys. It's not given. We didn't even have to find it. I just know that this is the work done. So this equation does not give us the final direction of work done. It just tells us, okay, force component parallel to delta X is whatever that value is. So this is what it tells us. It doesn't give us a vector, okay? So work is positive if it is in the same direction or 0 to 90 degrees, or equal, not equal, 0 or less than 90 degrees. And if it is greater than 90 and less or equal to 180, then it will become negative. Kenapa tak boleh equal to 90? Because it becomes a 0. Okay, so kita hanya nak parallel component. If my F hanya ada perpendicular component to the delta X, let's say this is F and this is delta X. So work done would be F cosine 90 delta x, and this would give me a 0. So there's no work done when there's no parallel component to the displacement. This is why dia cakap it is less than 90 ataupun greater than 90. It's not equal. Simbol equal tu tak ada. Yang ni simbol equal or less than kan. Yang ni tak ada equal tu. It's just bigger than ataupun less than 90. It can't be equal to 90. When it is equal to 90, it is perpendicular component to the displacement. Therefore, work done is going to be 0. Okay, so that is your recap. Last time we talked about this one ke tak? I forgot. Let's just go over it. So if my displacement is to the right and I have an F component in this way, I resolve my F component. Alamak. I resolve my F component. I have Fy over here and Fx over here. So Fx is in the same direction as delta x. Therefore, I would have positive work done. And this one is obvious. The force is in the same direction as displacement. So you would get positive work done. This guy, when I resolve it, I have a positive Fx ataupun an Fx component to the right. This is the same direction as delta x, positive work done. This guy, dia ke bawah macam ni, but if I resolve it, it goes to the right. This guy is also to the right, so I would still get positive work done. How do you know whether it's positive or negative work done? Your force and displacement are in the same direction. Mula-mula condition dia is kena parallel component. Okay, so this is yang paling penting lah untuk dapatkan work done yang not equal to 0. The second condition is if F is in the same direction as delta x, then you would get positive work done. Vice versa. Vice versa maksudnya F tak sama direction delta x, therefore work done is negative. So macam mana nak tahu dia positif ke negatif? Resolve your F. Tahu, you need to know what the angle is. This guy is F and X, angle dia equals to 0. Yang ni angle dia, tak ada. Ni angle dia Fx, F cosine theta. Sebab X dia macam ni kan. So yang ni pun resolve, Fx, macam tu. Okay, walaupun dia nampak pelik-pelik, resolve it first and then you will know whether it is in the same direction with X or not. Okay. So this is when it is not a positive work done. This is negative work done. For example, my delta x is to the right. My displacement is to the right. The motion of the object is to the right. Okay, saya tolak barang. Motion dia ke kanan. Saya tolak barang. Tapi saya tolak barang dengan force macam ni. Pelik lah. Tapi it is moving. I don't know why. So ada situasi macam tu, and macam mana nak kita nak tahu work done tu positif ke tak, kita resolve dulu. Force, when I resolve it, it becomes Fy over here, Fx over here. We have a parallel component to displacement. However, it is in the opposite direction. Therefore, our work done is negative. Sama juga, our F is here, resolve it. This is Fy, this is Fx. Fx terbalik dengan delta x, negative work done. And then this one is obvious, negative work done. Kalau dia tak sama direction je, negative work done. And then this guy, resolve it. Fx is this way. We have a parallel component to delta x, tapi terbalik. Negative work done. Okay, sama juga. Negative work done over here. Okay, so work can be positive and negative. I already showed you that. Positive if the component of force and displacement are in the same direction, and negative if the component of force and displacement are in the opposite direction. So let's take a look at this piano. So for this piano, we can draw the free body diagram. We would say this is mg, which is the gravitational force, and this guy is pushing the piano, so we have a pushing force. We have a pushing force. So the pushing force, if I wanted to draw my free body diagram, I would write it like this. Okay, and what if my piano is moving to the right? Sebab piano ni berat sangat, so the guy pushing the piano is not using enough force to move it to to move it up the incline. So the piano keeps on sliding down. Boleh situasi yang saya tengah tolak tapi berat sangat, so saya ke belakang. So the motion is down the incline. Motion is down the incline, therefore this is your delta x. So what is the work done on the piano? By the pushing force. The pushing force is parallel to delta x. The pushing force is parallel. Okay, pushing force arah ni kan. Delta x arah sini. It is parallel but in the opposite direction. Therefore, we have negative work done. What about the gravitational force? Force and displacement will give us work done. So what about gravitational force? I need to resolve the gravitational force. Okay, so I would have mg sine theta, and mg sine theta is going to be parallel to delta x. So in this case, kalau saya nak lukis balik, so this is mg sine theta, and then your delta x is also this way sebab dia piano tu is sliding down the incline. So this guy, this is your force, your parallel component to the displacement, and this is your displacement. They are in the same direction, therefore your work done is positive. Okay, so you have different forces and you have to know the contribution from each force on the work done on the object lah. Okay, so we had 1 and 2. What if I included friction? So macam mana kalau kita ada friction? So if I had friction, I want to ask you guys, what is the work done? What is the work done by friction force on this piano? What would you guys say? Is it a positive or a negative?
Positive.
Positive. Why is that?
Same direction with the delta x.
It is the same direction as delta x, betul. So walaupun dia friction ni macam selalunya menyusahkan kita kan, tapi in this case the friction is in the same direction as the displacement. Therefore, friction is doing positive work on the piano. Okay? So kena tahu dia punya direction. So ini kita dah buat dah. Okay, so what if you have multiple number of forces acting on an object and you want to know what is the work done? So kita cakap pasal gravitational force punya work done, we talked about frictional force punya work done, and we also talked about the pushing force punya work done. So how do we combine all these forces together and how do we combine all these work done together? So here dia bagi contoh kat sini, work done, the total work done is mg dot d. In this case, d is your displacement. Okay, ataupun delta x lah. Tak tahu kenapa dia pakai d. So mg dot d, where this is, we only want the parallel component in displacement, in the direction of displacement, and this is the pushing force, and then this is the reaction force, and this is the friction force. Okay, so for work done, kita tahu, we know that the first thing that we need to do is find the parallel component. So let's look at this diagram. Find the parallel component. Let's use green. Nampak tak kalau green? Okay, so the parallel component, so this is your displacement, D. Okay, I hope you guys can see that. Let me make this bigger. So that is your D, your displacement. So you are moving this box to the right and it reaches this point. So daripada sini ke sini adalah jarak D. Okay, so that is your displacement. So you have several forces acting on an object on this box. How do you determine the forces? You have to draw the free body diagram. So this is your reaction force, pulling force, friction force because it's not a smooth surface, and you have your gravitational force. So kita nak tahu parallel component dulu. So kita resolve dulu. So this is going to be P cosine theta. What about the component for reaction force? How do I find the parallel component for reaction force? What is the parallel component of reaction force with respect to displacement here? Come on guys, this is like chapter 3.
And cosine
Hmm? And
cos 90.
cos 90. Tadi siapa jawab Aida
Right.
Oh, Rai. Okay, thank you, Rai. So Rai is saying n cosine 90. So betul ke? Is that the parallel component of reaction force? Does everyone agree?
Sine.
Apa dia?
And sine 90.
It should be n sine 90. Okay, so it's n sine 90. So it's n sine 90. Okay, so any other answers? So what is the parallel component of reaction force here? So everyone is confused. Okay. Oh, ada orang jawab dekat chat. Let me see. MG. MG. MG ke bawah. Parallel ni selari. Maksud dia selari. Okay.
P sin theta.
N sin theta. Oh, MG sin theta.
P sin theta.
P sin theta. P sin theta would give us somewhere here. But I was asking what is the parallel component of N. Okay, P sin theta ni perpendicular component of P. So, okay, I'm going to give you guys the answer. So, N is 90 degrees to displacement, right? N is 90 degrees to displacement. Therefore, if a force is perpendicular to displacement, the work done is going to be 0. If F is perpendicular to delta X, work done is going to be 0. So betul N cosine 90 tu betul, or you can just say it's going to be 0. There's no contribution. Sebab angle dia perpendicular to displacement. When N cosine 90 is equal to 0, you can put it into the equation, no problem. So it becomes N cosine 90 delta X, which is 0. Okay, so there's no contribution to work done if a force is perpendicular. Tolong ingat this point. Okay, that was a trick question saya tanya. So next time kalau ada exam tanya, find the parallel component of reaction force. Then you know it's 0. Perpendicular forces tak ada contribution to work done. Okay. Perpendicular kita nak parallel sahaja. Okay. So I hope everyone took note of that. That was a trick question. So P cosine theta is a parallel component to displacement. So we like that. So kita cakap, oh this one ada value. So P cosine D. So this becomes P cosine theta D. I don't know what theta is. This guy becomes mg. What is the angle between mg and delta x? What is the angle between mg and delta x? So yang ni n cosine 90 D, mg macam mana?
mg pun 0.
mg cosine 0. Oh, mg pun 0. Is that what you're saying? Okay, mg pun 0, betul. Because it is perpendicular. Perpendicular tu apa? 90 degrees. Kita punya x ke sini, mg kita ke sini. This is 90 degrees. Kosong. Work done is kosong. So mg cosine 90 D. Ataupun perkara yang paling saya suka buat ialah buat sesuatu benda jadi kosong. Become kosong. Okay, what about friction? What should be the angle between friction and D?
180.
180, betul. Friction is this way, your x is the other way. So angle between them is 180. So this would be F cosine 180 times D. And this would give me a negative f times D. Sebab cosine 180 ni minus 1 eh. So let me rewrite that. So F minus 1 D. Yang ni adalah spesifik untuk this equation eh. So what do you get for your total work done? You get P cosine theta times D. Tak tahu theta apa, tapi ada value, is not 0. And then F times minus 1 times D. So you add these two guys together, that is your total work done. So what can you conclude here? Hanya parallel forces will contribute to the work done. Only parallel forces. Perpendicular force will give you a 0. Okay? Okay, so this is the first approach. What if you wanted to use F net instead? You don't want to do one by one. You want to do F net instead. So you can do that. So let's do that. So F net that we are interested in is only the parallel component because itu sahaja yang akan bagi kita, alamak kenapa saya padam? No. Okay. Sebab itu saja yang akan bagi kita work done kan. Okay, so F net yang I'm interested in is only net in the fx ataupun fx net. Net in the fx itu sahaja yang akan contribute kepada saya punya work done. So net in the fx and t. So this is your F net. So what is your F net in this case? Ataupun net in the fx. So net in the fx I have minus f and I have positive p cosine theta. So net in the fx is equal to p cosine theta plus minus friction ataupun minus friction terus lah. Sebab arah dia berbeza kan. We've learned this in chapter 3. So net in the fx is p cosine theta because it's to the right and minus friction because it's to the left. So this is your net in the fx and then you put this into your equation. Okay, put this into your equation. Let me rewrite this, net in the fx. So this becomes p cosine theta minus f and you would get something that is force punya value and then darab dengan d. So that is how you use the net fx. Kenapa saya tak letak cosine theta ni? Sebab cosine theta tu ialah net fx lah. Kita nak tahu semua yang dalam x direction sahaja. So kalau saya nak tahu, kita nak letak cosine juga, okay. Nak letak cosine juga boleh. Let me use a different color. So an F net cosine theta akan jadi P cosine theta minus F cosine 180, sorry, plus F cosine 180. But I feel like this is going to be confusing to some of you. So saya prefer korang cari net in the fx ataupun net F that is parallel to your displacement. Cari macam ni, use the skills that you got from chapter 3 and put it as your F lah in here, okay? So terus akan dapat jawapan. So tak ada pening-pening kepala, positif ke, negatif ke. Kalau pakai equation F net cosine theta ni kena fikir positif negatif macam lain pula. So use the skills that you have learned in chapter 3 and plug it in. Okay, so net in the fx only. So any questions so far? Everyone okay? Still awake? Okay, alright.
Okay.
Okay, so questions that you can be asked when solving problems. So what are the forces acting on the object? So we know this already. This is your free body diagram. And daripada free body diagram, kita boleh tentukan what is the net in the fx. And then in which direction is the net force? So from your net in the fx, you found out that you have a positive value, contohnya positive 10. You resolved everything, this guy becomes, ya Allah kenapa terik sangat warna ni. This becomes mg cosine theta and this becomes mg sin theta. And then this is ni apa? Pushing force. And then what else? Kenapa dia hit me? Many reaction force. Pushing. Biru ni saya tak tahu apa. Okay, so let's say FP minus FP, cakap mana satu positif lah. Kita cakap ke atas positif lah. So FP is positive minus mg sin theta. And then what else? We have other contribution. We don't have friction. So kita akan cakap FP minus mg sin theta is positive 10. And this is your delta x is also going up the incline. So you have a positive 10 and you said that the motion is going upwards and this is also positive displacement. So you would know that your work done is going to be positive. So because your direction of net force is in the same direction as your displacement. So adalah kegunaan positif dengan negatif semua tu. You get to know if it's in the same direction or not. Okay. So just now we talked about forces yang constant. For example, the pushing force was 10 Newton. So we were assuming that the pushing was not going to change in force. Bila orang tu tolak, dia tolak 10 Newton je. Padahal tak adalah macam tu kan. That is not what happens in reality. But this is the assumption that we make to make our life easy. So other instances is the friction is constant over the surface when it's not. Sometimes kita ada tempat yang lagi kasar, kadang-kadang tempat ni lagi licin, so friction tak sekata. So we are assuming these forces are constant when in reality they are not. So ada setengah force yang kita tak boleh assume dia constant sebab dia memang berubah memang dia berubah banyak gila. So contohnya, benda yang kita tak boleh cakap constant adalah elastic force of a spring. Okay, elastic force of a spring and also the electrostatic force between charges. I'm not going to cover this one. This one kita akan belajar next semester. So kita akan cover elastic force of a spring. So the equation of elastic force of a spring is given as F equals to minus Kx, where K is the spring constant. So it depends on what kind of spring you have. So kalau sometimes you have a spring that is hard to extend and sometimes you have a spring yang sangat lembut and you can extend it very easily. So this K value gives you the property of that spring, whether it's hard or whether it's, I wouldn't say it's soft, panggil apa, whether it's hard or easy to extend. Okay, so the K is the property. It depends on what type of material your spring uses. So that is your K. And X is the extension or compression. Extension or compression of the spring. Nanti kita akan tengok of the spring. So typically we assume X is displacement. This is also displacement, but we measure this displacement with respect to the original position. For example, I put a marble. What is this marble? I put a marble at the end of a spring, okay, and saya tarik, saya renggangkan spring tu, I extend the spring, so it becomes longer, and this is where the marble ends up. Saya pegang, saya tahan. So the displacement is measured by taking the initial position to the final position. So this is the change in the displacement lah. Okay, so this is your X. So this is where you put the X into your equation, and K is typically given or you have to find it, but it depends on the type of spring that you use. Now, what else? What is actually F? What is actually F when we're talking about springs? Okay, so when we're talking about springs, we have, let's say I use my hand to stretch it, right? Let's draw my hand really quickly instead of a marble. So I'm going to pegang marble ni lah, okay? This is my hand. I'm stretching the spring, but I'm tugging on the marble to do that. Tak kisahlah, kalau tak ada marble tu pun tak apalah. Saya akan tarik spring tu. So this is F applied. This is the force that I'm applying to the spring. This is the force that is applying to the spring. So you would notice when you are extending a spring, it is very hard to extend it. It's very hard. Because why? Because there is a force acting in the opposite direction. So I'm extending it to the right. Ada something else that is going to be pulling it in the opposite direction, which is why it's very hard to extend it. So this is called Fs ataupun the force by the spring ataupun the elastic force of the spring. So the more force that you exert on the spring, the more force exerted back on you by the spring. The spring does not like you trying to pull and tug whatever. The spring does not like that. The spring wants to go back to its original position. So let's say saya tarik ke kanan kan, dia cakap tak nak, dia nak ke kiri balik. So what it will do is, it will go back to the left side. So what is Fs? Fs is this guy minus Kx, and F applied will be Kx. Okay, so F is minus Kx. F applied, which is what I'm exerting on the spring, is going to be Kx. Dia akan sama sebab this is Newton's third law. Saya apply 10, spring tu pun apply 10 balik dekat saya sebab dia tak nak. Dia nak restore back to its original position. And how does it do that? It has to apply the same amount of force to overcome the force that I am exerting. Okay, so this force yang suka patah balik ni, yang tak suka berubah ni, is called a restoring force. It's called a restoring force. Now after this, if you hear about restoring force, maybe in your degree ke apa ke, you would know that it is a force that wants to go back to its original position ataupun original state. A force that keeps the system back to its a force that wants lah, bukan keep. Sebab dia akan ada perubahan juga. A force that wants. Macam ada perasaan pula. A force that wants the system to go back to its original state. Mula-mula saya dengar perkataan ni, saya macam apa benda restoring force ni. Tapi this is what it means. It wants to go back to its original state. Ni bahasa yang paling mudah lah saya boleh ceritakan. It wants to go back. Why? So this is what dia nak restore. Restore means apa? Kembali kepada asal kan? Restoring. Okay? So it is a type of force yang akan oppose any changes that is applied to it. In this case, saya tarik by 10 Newton, dia tak suka. Dia akan apply 10 Newton juga tapi in the opposite direction. This is why our equation, satu ada negatif, satu tak ada negatif. Okay? So the work done untuk kira, the work done of the force, the work done of the elastic force ataupun the applied force is given by integration. Because why? The force is not going to be constant. The further, how do I say this? Tengok balik equation ni. So F is equal to Kx, right? So the further away your displacement is, the bigger your F. So if I plotted this in terms of graph, it would look like this. F versus X. So the higher your X, the higher your F. The smaller your X, the smaller your F. F is proportional to X, which means that it is not going to be constant. It is not going to be constant. So kalau X kita 1, F maybe 2. X kita 2, F kita maybe 4 because it is proportional. Dia akan increase accordingly. So this is called a variable force. Force yang tak constant lah. So when we have a variable force, we need to do integration. Do you guys have to do integration in our class? In this class? No. You just have to memorize the equation. So, but you have to know that the equation for a variable force comes from integration, and it would lead us to getting this equation. Mana pergi? Sekejap, sekejap. This is not it. Sekejap. Okay, so dia dah buatkan integration. So W, if we are stretching the spring from X1 to X2, this is your F. This is your displacement over here. You are integrating the force with F applied. You are integrating the force with respect to the distance that the spring extends by ataupun compresses by. And kx squared divided by 2, this is after integration, and then you plug in the values. So you would get, kenapa terbalik? 1 over 2 kx2 minus kx1. Terbalik. So, but this is not the point of this slide. Kejap. Okay, tak apa. Kita akan go with it. And then what happens for a force for yang electrostatic tu kan? I told you electrostatic force is also a variable force. Same thing. This is the equation for force. You put it into your equation. You integrate it with respect to the change in displacement. The displacement in this case is the distance between the two charges. I wouldn't say this is important to remember now sebab nanti kita akan belajar in detail later. But you have to know that for a variable force, you need to do integration with respect to the positions ataupun the displacement to find out what is the work done. Okay, so the graphical representation of work done by a force is given as the following. So this is when you have a constant force. This is a constant force. The force does not change. Walaupun height dia increase, this is height. Walaupun height dia increase, value dia tetap sama. Value dia tetap sama, which is 5 Newton, let's say. But in this case, we have seen this happen, F equals to Kx, where when X increases, our F also increases. So this is the graph. And then we also have this type of graph, but I don't know what the equation is. So what it's trying to say here is your work done can be calculated by measuring ataupun determining the area under the curve. Okay, you can find out what is the work done by measuring ataupun calculating the area under the curve. So let's say I want to know, hey, what is the area from 2 to 5 meter when I am applying a force of 5 Newton. This is in Newton and this is in meter. So I can use the area of this shape. So work done is equal to 5 times with 5 minus 3. This is 3 and this is 5. 5 times 3. Okay, 5 minus 2. Nak buat 5 minus 3. 5 minus 2 ataupun 3 lah kat sini. So you will get 15 Newton meter or joules. So this is the area that you get. So force times with height gives you Newton meter or joules. So this is work done. What if we have a slanted line macam ni? Sama juga like the ones that you have learned before. Just use, this is a square, carilah value dia apa. So A1, area number 1, area number 2, use the formula for a triangle. Work done will be A1 plus A2. And then for this guy, ini susah sikit lah. Kalau rajin lah, kalau ada soalan macam ni, boleh buat these small shapes until it fills out everything. So you will get the answer lah. You will get the answer, but it's going to be hard. So selalunya kalau ada curve macam ni, orang integrate terus lah sebab selalunya malas. But if you like doing the shapes thingy, you can do that as well. It works. So the question is, what if the graph is below the x-axis? What do you do? So let's say you have another graph. Okay, oops. Okay, you have another, kenapa saya punya line sangat? You have another graph. And wow, this is like epic gila sangat dia. So this is your force. Sorry, this is F. And this is your height. And your graph is like this. Let's use a different color. The graph is like this. So dia ke bawah. Boleh ke nak kira dia punya work done and how do you do it? So the answer here is the top part will become positive area and the bottom part will become negative area. So, ataupun work done lah, I would say work done. Positive work done and negative work done. Okay. So, jawapan di kat sini akan jadi work done number 1 and work done number 2. So, total work done is W1 minus W2. So, this is your net work done. For a graph, yang line dia ada ke atas x-axis and below the x-axis. So, this guy, it is bounded by the x-axis. So, cari dekat sini. Okay, so ada cases ada cases where the graph is like this, kan? So dia dah cari yang ni betul dah. So this is A1. Lepas tu dia pergi cari yang ni kat bawah sini. Sebab graph ni end dekat sini. Salah lah. Mana boleh kira kat bawah ni? Bawah ni endless kot, infinity. Minus infinity. So if you kira daripada sini ke bawah sini, I don't know what that value is. So it's wrong. Do not do that. The area should be bounded by the x-axis over here. So please remember that. Jangan buat kesilapan. Walaupun dia nampak macam kat sini macam seronok je nak kira kat sini kan. Tak payah, jangan seronok sangat. Jangan kira kat sini. No, this is wrong. Walaupun dia end kat sini, dia letak nombor minus 10. Oh, sedap pula nak kira kat sini. Jangan Selalunya tu trick question. So always find the area bounded by the x-axis. Atas x-axis positive, bawah is negative. Okay. So let's take a 7-minute break and then we will go to example lah. Okay. This is the example that we're going to do in after our break. So let's come back at, right now is 2:53. So let's come back at 3 p.m. Kalau ada soalan boleh tanya. Otherwise, please take your break and we will continue with this example. Or you can start early. Okay, dah pukul 3 dah. No questions from anyone? Okay, so everyone understands so far. That's good. Let's continue with this example. So I hope everyone is back and awake. Kalau tak, wake up, jangan tidur. Okay, so let's do this example. PBL 4.1, I believe this is also in your textbook. Page, let's see, page apa? This is going to be page. Oh, this is PBL 4.2. So this is page berapa ni?
56.
Oh, 56 kan again. Oh, saya telah tengok. Okay, so this is page 56 in your module book. If you want to do it in your book, boleh. Okay, sorry. So a block of mass 25 kilogram is pushed 1.2 meter along a frictionless horizontal table. So let's draw our table. So they didn't tell me when I was doing engineering or physics that I had to be good at drawing. Tapi sekarang ni hari-hari kena draw. So kena pandai drawing juga sikit. Okay, baik, tak apa. Lukisan buruk pun tak apa. Jadi macam saya. Draw. Where is my pen? Okay, so this is our horizontal. Saya tahu lah kenapa hari ni. Horizontal table. It's supposed to be horizontal. And we have a block of mass 25 kilogram. Ni dia bukan melengkung it's supposed to be horizontal. So this is 25 kilogram is pushed 1.2. So if I take this point as my center, it is pushed by 1.2. So this is where it's going to end. So this is 1.2 meter. This is our delta X. Okay. So it is pushed frictionless, so tak ada friction, by a constant 36 Newton force directed below the horizontal, directed 35 degrees below the horizontal. So if I were to draw this force, we draw our imaginary force first, imaginary axis, it is going this way. And this is 35 degrees below the horizontal. So boleh bayangkan saya tengah push macam tu push dari atas tapi force tu ke bawah. So this is the direction that it is being pushed. So force ni ke bawah macam ni tapi 35 degrees with respect to the horizontal table. Determine the work done by the applied force. So this F is equal to 36 Newton. And then tanya the normal force exerted by the table. So this is going to be our R, the force of gravity, mg, and the net force on the block. Okay, what do we know about net force in work done? We need to know what is the F parallel to delta X ataupun net Fx to delta X. We don't want the entire F net. Kita tak kisah pun pasal Fy sebab perpendicular forces will give us 0 work done. Soalan minta work done by force apa. Okay. So we have reaction, we have mg, we have force, the pushing force. We don't have friction because it is a frictionless horizontal table. Okay, so let's continue. We know our displacement. Tapi kita kena cari work done for each forces first. Okay, so A is the applied force. We need to know what is the component parallel to displacement delta X. So this is going to be work done by Fp is equal to F cosine 35 times with 1.2. No, I should write the general equation first. Let me write the general equation. F cosine theta delta X for you guys in your reference. So this is going to be 36 cosine 35, this is Fp, and this is going to be 1.2. So this is the work done by the pushing force. B, the normal force exerted by the table. So this is the normal force. It is 90 degrees to the displacement. What do I know about this? What is the work done?
0.
Is equal to 0. Or if you are feeling fancy, you can write the equation. So this is going to be R cosine 90 times with delta X ataupun 1.2. So this is still going to give you 0. Jangan pakai sin, pakai cosine. Sebab equation dot product adalah cosine. So this is going to be 0. And then for C, the force of gravity, mg, sama juga. Fg is going to be 0. But if you're feeling fancy, lukislah. Lukis pula, tulislah equation dia, boleh. If you don't want to write the equation pun, boleh juga. So it's going to be mg. So this is, hello. It's going to be mg cosine 90. Kenapa bukan sin? Sebab dot product adalah cosine. F dot delta X adalah cosine. Tak ada sin kat sini mg cosine 90 times with 1.2. So this is a 0, 2. Now it's asking what is the net force on the block? What is the work done by the net force on the block? Okay, so I told you before what we need to do when we are trying to find the net force for work done is kita kena cari parallel force sahaja. So what is the parallel force acting in the displacement? It is only this guy, Fp cosine theta. So net in the Fx is only, yang ni je lah, tak ada komponen lain dah. So F cosine theta. And then work done by the net force is going to be F cosine theta, 36 cosine 35 tu lah, times with 1.2. Let me write the general equation. Delta X, and this is going to be 36 cosine 35, 1.2. This is your answer. Okay, boleh pakai calculator sendiri. So let's see the answer. So applied force, kita resolve F cosine theta, 36 cosine 35 times 1.2. The normal force, 0. Force of gravity, 0. Sebab dia 90 degrees to the motion. 90 degrees to the motion. So akan dapat kosong. Then the net force, we only have this guy yang ada value. Yang lain semua kosong. So jawapan dia akan sama dengan yang kat sini. Which is what we got. Net Fx is only F cosine theta, sedarak dengan displacement, and this is the same as A, which is what they are seeing over here. Okay. So any questions about this example, or is everyone okay? Any confusion?
Okay.
All right, no confusion then. So ada confusion, please interrupt me. Kenapa dia stop? Oops. What happened here? What happened to my slide? Kejap. Okay. Okay, so now we go into our next subtopic. Tadi kita belajar pasal work done and its example. So now we're talking about mechanical energy. What is energy? Oh, energy is the capacity to do work. So it has the same unit as work done. It has the same, this guy has units of Newton meter or joules. Energy also has the same units, which is Newton meter or joules. So dia sama, tapi energy is the capacity to do work. So you need energy for you to be able to do work. For example, if I don't have any energy, I won't be able to teach. So teaching is work done, right? So I need energy. So how do I get energy? I eat food, I sleep, I drink water. So this is me getting energy. So energy is then used to do work. So dia unit dia sama, tapi it is macam tu lah, dia energy, kita akan pakai energy untuk buat work. Okay, so you need energy to do work, yes. So positive work means that you are gaining energy. So if I'm eating I can say that the food is doing positive work on me. Therefore, me as a system is gaining energy. So saya makan, I'm gaining energy. So I am gaining positive work. The work is done by the food on me. But if I am cutting a tree, so I don't want to cut a tree. So let's say one of you guys is cutting a tree. Where is it saving now? Saya berehat sekejap. Okay dah, habis dah. So let's say one of you guys is cutting a tree. You cut the tree, you are doing work on the tree, you are losing energy. When you are losing energy, you are doing negative work on yourself because you are losing energy. But when you tebang this pokok ataupun you're cutting this tree, you are doing positive work on the tree. Okay, and the tree, kiranya you guys get negative work because you're losing, you become tired. But this guy gets something in return. It gets being cut. So this is positive work done. So apa-apa benda yang dibuat, saya cakap, benda yang kita buat kerja, how do I say this? So let's say I have a ball. Saya ketuk-ketuk ball ni. Saya ketuk-ketuk ball ni tanpa sebab. Tak tahulah. Saya ketuk-ketuk, I'm exerting a force. So positive work is done on the ball walaupun it's a negative action. Positive work done, positive work on the ball. And because I'm doing this, right, I'm losing energy, I become tired. So negative work is done on me. So benda yang losing energy, negative work. Benda yang gain energy, positive work. So macam mana kita nak tahu ball ni gain energy ke tak? So when I'm buat macam tu kan, I'm actually transferring energy in the form of maybe potential energy, maybe kinetic, bila saya ketuk-ketuk dia bergerak, so ada kinetic energy. So energy tu datang dari saya, so I am getting negative work. The ball gets the energy that I am transferring to it, and it gets positive work, and that energy becomes something else. For example, it can move, so it becomes kinetic energy, ataupun dia melantun, it becomes potential energy. So this is something that we will learn in the next few slides, hopefully. Sempat tak? Sekarang berapa? Okay, sempat. So this is what we're going to talk about, the conservation of energy and also the panggil apa? Transformation of conversion of energy lah from one state to the other. For example, saya ketuk-ketuk kan, saya ketuk-ketuk, this is that's kinetic juga. Tak apalah, nantilah kita akan bincang dengan lebih detail. Okay, so energy is a scalar quantity as well sebab sama unit dengan work done. So it is also in joules or Newton meter. So the ones that we are going to focus on, mechanical energy yang kita akan cerita nanti, yang convert ni, is kinetic energy, gravitational potential energy from gravitational force, and elastic potential energy from F equals to Kx yang kita belajar tadi. Okay, so elastic potential energy, equation ni datang pada work. So kita perlukan force. So kinetic energy je 1/2 mv squared bla 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 tu kan, itu kita dah tahu dah. Tapi gravitational potential energy datang daripada force, gravitational force, and elastic potential energy datang daripada F equals to Kx ataupun minus Kx. So these are the three things that we will cover in this topic. So kinetic energy is the energy of an object associated to its motion. So when we have movement, when we have pergerakan, you would have kinetic energy. The object would have kinetic energy. So I can say that this mass of ball, this ball of mass m that is moving with velocity v will have a kinetic energy of 1/2 mv squared. So this is the equation if you want to know the kinetic energy of this ball. However, what if, kenapa dia macam ni? What if our velocity changes? The velocity of the ball changes. So kita punya ball ni, ball tadi, kita cakap dia constant lah konon-kononnya. Tapi ada situasi where the ball changes in velocity, which means that the u is not equal to its v. It started with 10 and then maybe it ended up with a velocity of 5. So there is a decrease in velocity. Ataupun it starts with 10 and it ends up with a velocity that is higher than the initial velocity. So 10 dia jadi lagi laju, tak tahu kenapa dia jadi lagi laju, so it becomes 20. So when you have these changes in velocity, where the velocity is not constant, you would have acceleration. When you have acceleration, you would have force. Because when we multiply mass with acceleration, when we multiply the mass of the object with the acceleration that that is happening, we get force. So work done times force and displacement. So you substitute MA into this equation, and A is V squared equals to U squared plus 2AS. We rearrange this to become V squared U squared over 2S. This is your A. You substitute that into this equation. So you would get mv squared minus u squared over 2s times s. So this cancels out. You would get 1 over 2 mv squared minus 1 over 2 mu squared. So the kinetic energy changes. And the change in kinetic energy is equal to work done. This is our equation that we need to remember. Okay, so again, kinetic energy is just 1 over 2 mv squared. We saw that earlier. That is Ke. When you have a change in kinetic energy, this is the equation and it is equal to work done. So can I say this is equal to work done? No, this is wrong. Work done only happens when we have change in kinetic energy. Kalau tak ada change, tak ada. Okay, moving on. So this is known as the work energy theorem. So work energy theorem tells us that the work done on an object is K final ataupun kinetic energy, the final kinetic energy minus the initial kinetic energy. This is known as the work energy theorem. Kena ada perubahan KE. Okay, this is why we have the final and initial. Okay, so when we have positive work done, it would mean that we have a positive KE. When we have negative work done, we would have negative KE. So what does positive and negative KE mean? So if we look at this equation, kalau nak jadikan dia negative, let me factor this out first. 1 over 2m, I factor it out because it is the same. So this becomes v squared minus u squared. So if I wanted for this guy to be a negative, what is the condition for v and u? How do I make this guy negative? So the answer is the v must be less than u. Maksudnya it is going to be slowing down. Kalau u lagi besar dari v, maksudnya kita start laju berakhir dengan slow velocity. So this guy ataupun the object is slowing down. So I would get negative work done on the object that is slowing down. So this becomes v that is less than u ataupun it is slowing down. And for positive KE, so this is going to be positive work done. What is the condition to get positive work done based on this equation? It means that V needs to be greater than U. V greater than U means that it is speeding up. Okay, you start with 5, you end with 10 velocity. You are speeding up. So here, V needs to be bigger than U. And this is speeding up. Okay, so this is what the work energy theorem tells you. If you have positive work done, it means that the change in kinetic energy is positive. It means that your object is speeding up. If you have negative work done, change in kinetic energy is negative, you are slowing down ataupun the object is slowing down in terms of velocity. Okay. Okay, kita cakap pasal ni. So that is on work done in relation to kinetic energy. Now we move on to potential energy. So the energy of an object is associated to its position. So gravitational potential energy can be due to gravitational force, like I told you before, Fg, and elastic potential energy is due to elastic force. So dua-dua ni ada kaitan dengan position. For example, I have a ball. over here. This is on ground. So H equals to 0. So I bring it up by H. Oops. So I bring it up by H. So Y equals to 0 here. Y equals to H over here. Therefore, my SY is equal to H. By H minus 0. So I'm bringing this ball up by a height of H. And there is a change in position of this ball. So the energy down here, denoted as U, this is potential energy, is going to be U1 and this is going to be U2. They are not going to be equal. U1 is not going to be equal to U2 because they have different heights. So this is what we are going to learn about gravitational potential energy. Based on the height, they would have different potential energy. So lagi tinggi, lagi banyak potential energy. And then for elastic potential energy, this is related to our F equals to Kx, remember? So this is also related to position. So spring kita extend and then ada displacement. So it's related to position as well. So both of these energies are related to position. One is related to the height. The other is related to extension or the compression of the spring. Dua-dua position. Okay. So kenapa saya potong ni? So gravitational force, tak payah belajar lah, kita dah tahu lah pasal gravitational force. Let me rub this off. Sekejap, 2 minit. Apa tu? Iklan sekejap, saya penat. Okay, so let's continue. So gravitational potential energy. Consider an object of mass m. Okay, bola ni lah. So we are talking about this ball. Let me use a black color. We're talking about this ball. Is raised from ground level. Okay, boleh dekat sini. This is ground level. H y equals to 0. And then it is raised to a height of h. Okay, so basically dia naik by a displacement of h, right? So this is the work done against, So when we are talking about potential energy, gravitational potential energy, we are trying to relate it to gravitational force. But gravitational force is supposed to be constant, right? However, untuk work done for gravitational force, kita kena pakai integration. Sebab, saya tak ingat sebab dia apa. Sebab apa? Well, okay. I told you guys that the gravitational force is only constant when we are close to the surface of Earth, right? And it gets weaker as we go further away. So dia sebenarnya variable force lah. Dia variable force tapi kita assume constant sebab semua orang berjalan atas Earth. Kita tak assume orang terbang. So that is why we see it as constant. Tapi sebenarnya dia variable force. Okay, so kita kena integrate. So dia akan menyusahkan hidup kita sikit tapi tak apa, kita hafal je equation ni. You don't have to memorize how to integrate. I won't ask you to integrate an equation in physics. That's for your math subject. Okay, so for physics, kita hafal equation, apply it correctly. Apply it and understand the concept. So for gravitational potential energy, it is actually work done. For gravitational potential energy, it is, we're not talking about gravitational potential energy yet. We're talking about work done. So the work done against gravitational force is mgh. Kalau tengok kat sini, tulis mgh minus mg kosong. So mg kosong, kosong lah kan? Darab dengan kosong akan jadi kosong. But what if we did not start at ground level? What if we started at y equals to 2 ke? It's not 0. So this becomes h minus mgh minus mg2. So work done is still the change in energy. Previously we talked about work done is equal to the change in kinetic energy. Now we're saying that work done is actually the change in potential energy. So this is W equals to delta U. So so U is actually mgh, and work done is delta U or mg delta h. Ke is 1 over 2 mv squared. Work done is the change in Ke or 1 over 2 mv squared minus u squared. Macam tu. Ataupun Ke final minus Ke initial. So this is the point that it's trying to make. The work done is actually the change in energy. Work done is the change in energy. You have your equation for energy, no problem. Ke is 1 over 2 mv squared, U is mgh. But when we are talking about work done, there needs to be a change. Fakta, there needs to be a change. So delta U ataupun delta Ke. So that is your next equation yang kena hafal, U equals to mgh. Okay, so U equals to mgh. How do you know what is the work done on the object? So at U1, at U1, it is mgh1, and at U2, it is at mgh2. So let's say you want to know what is the work done if I bring this ball from here to here. So this is state number 1, this is state number 2. What is the work done that I'm doing if I bring this ball up from H1, this is H1, and to H2? So use your equation, W equals to the change in U. This means mg H2 minus H1, always final minus initial. So this would become, I don't know, H2, whatever that H2 is, and H1, let's say H2 is 5. And this is 2. You plug it in. Mass takkan berubah, G tak berubah dekat near the earth. So you just use that value. Mg, so what is H tadi? 5 tolak 2. Mass, apa-apa je lah, 2 and 9.81. So this is the work done on the ball when you are raising it from H1 to H2. Okay, work done is the change in U. Okay, next one. The work done to change the height of the object is the difference, the potential in the, yeah. Okay, so we know that. Apa yang saya kena highlight kat awak yang penting kat sini? Work and change in potential energy. Okay, so we talked about U, right? We talked about U and Ke. But what if we wanted to talk about the work done by the gravitational force? Okay, work done by the gravitational force. So before we talk about that, let me tell you, let me recap on what we have learned. So we know that work done is F dot delta X, and this means that the F must be parallel to delta X. Whatever the component of force that is parallel to delta X, you multiply. So that is work done, right? So if my F is like this and my H is like this, I would have positive work done. If my F is this way and my X is this way, I would have negative work done. So we learned about this previously. Now I apply it here. So my mg is going down. So that is my force. My mg is going down. That is gravitational force. However, I am bringing it up by h. I'm bringing it up by h. So F ke bawah, h ke atas. So if I were to draw it from a single point of view, so I can see that this is going to be my gravitational force and this is going to be my h. So they are in the opposite direction, or the angle between them is going to be 180 degrees. What does that tell me? What is the work done here? Is it positive?
Negative.
It's negative because it is in the opposite direction. Walaupun benda ni tengah berlaku dalam y-axis, it is still the same. Tadi kita cakap pasal x-axis when it is on the ground. Now we're talking when it is up in the air, but the same concept applies. So force ke bawah, displacement ke atas is opposite direction, therefore work done is going to be negative. So here, the work done by gravitational force is negative delta U. Negative delta U. Because remember, work done is delta U. If work done by the gravitational force is supposed to be a negative, we can say that this is going to be negative delta U. So what if I change this sentence? Instead of saying by, I say against. The work done against gravitational force. The work done against gravitational force. What does that mean? It means that I am applying a force that is going to be in the opposite direction of gravitational force. How does that look like? Let's draw it. Kalau kita cakap by maksudnya dibuat oleh gravitational force. Now I'm talking about a force that is going against the gravitational force. Maksudnya saya apply, F applied, kita ada F applied, tapi F applied yang terbalik dengan mg. Where have we seen this? We have seen this in a spring situation. You nak save lah tu. Siapa dah tahu dah perangai dia ni. Kejap pula. Okay. So spring, saya tarik, F applied. Spring tak suka, spring marah, dia nak pergi, patah balik. So this is Fs, F applied adalah terbalik. Tapi equation diorang sama. Equation Fs minus Kx and F applied is Kx. They have the same equation, only the direction is different. That's why they have the negative and the positive. In this case, I am applying a force against gravitational force, against maksudnya terbalik. So it should be equal to, F applied should be equal to positive mg. This is going to be minus mg. Okay, so Fg is minus mg. F applied is against mg, so it is positive mg. So dia sama konsep macam spring tadi. Dia akan terbalik. So when they are asking you what is the work done against gravitational force, against, terbaliklah. So instead of saying negative delta U, it would be positive delta U. Because we are moving this way, this is our height, and our F applied is also in the same direction. If I were to draw it within the same, from one single point of view, I can see that F applied is here, H is also going this way. Sama direction, angle adalah kosong. So you would get a positive work done. Okay, let me recap that. When I'm talking about work done by gravitational force adalah ke bawah. Tapi saya tengah angkat buku ke atas. So this would give me negative work done. But when I am applying a force against the gravitational force, sekarang ni bukan gravitational force yang buat kerja. I am applying, saya tengah angkat buku ni. So I am applying a force against gravitational force. Saya kena apply force supaya saya boleh angkat buku ni. Buku ni tak boleh angkat sendiri, saya kena apply some force. So I am applying F applied in the same direction as height. Therefore, I would get positive work done. So this is where U comes from. U datang daripada F applied sebenarnya. So this is your equation when you are talking about F applied ataupun the force against gravitational force. Okay. Kita cakap pasal ni dah. Let me see. So elastic force is proportional to the amount of deformation. That means that it is equal to Kx. The amount of deformation maksud kat sini ialah compress ataupun stretch. So Kx lah. Dia tu nama dia displacement of the spring. Kalau dia makin panjang ataupun makin kecil, compress. So that is related to X. Force depends on position only. This is also known as conservative force. Okay. That tu macam reading punya material sahaja. I believe that is also in your textbook. Let me see. Nama dia elastic force. Okay, so here it says F is the restoring force. Kalau saya nak cerita pasal conservative energy, conservative force, macam panjang pula. So I'm not going to tell you guys about that. So dalam buku dia cakap pasal restoring force. So if they ask you what is restoring force, you already know what that is. So conservative ni kita belajar kemudian lah. Okay, so Hooke's law gives the force as F equals to minus kx, where F is the restoring force. Where F is the restoring force and F is in the opposite direction of extension X. Dan ni adalah elastic force of spring. K is called the spring constant and value of K depends on the string. Okay, we already talked about this. And then this is F applied versus X displacement, either stretching or compressing. And when we increase X, therefore our force also increases because it is proportional. F is proportional to X. Macam mana tahu? Datang daripada equation ni. Okay. So again, this guy pun dia variable sebab kita punya force berubah mengikut displacement. Therefore, our work done is calculated using integration and therefore we would get elastic potential energy as the following equation. Mana dia pergi? Saya tak tahu kenapa slide saya dia macam ni. Macam pelik pula. Dia salah format. Consider an object attached to the end of a spring. When you stretch the spring, elastic force does negative work on the object. Okay, so let's talk about this one. Okay, when you stretch the spring, you are moving the spring to the right, right? So your Fs, when you stretch the spring, the elastic force does negative work on the object. Kenapa? Sebab angle dia adalah 180 ataupun they are in the opposite direction, therefore you would have negative work. You need an equal amount of positive external work on the object. So this is known as F applied. So when F applied is to the right and your extension is also to the right, you are doing positive external work that is stored as potential energy of the object. So this is where potential energy comes from. It is from the F applied that you put on the spring to stretch it ataupun to compress it. That energy that you give, you are giving that energy to the spring, disimpan. Dia ambil energi yang korang pakai untuk tolak ataupun tarik tu and it stores it in the spring in the form of elastic potential energy. So kat mana kita tengok benda yang similar happen? We saw that when we had a ball and when we move it upwards, it would have U. It would have a change in U. Datang, where does the change in U come from? It comes from me trying to lift the ball. I am applying force to lift the ball. The energy came from me and now it is being stored as potential energy. But in this case, it is called gravitational potential energy. Sama juga kat sini. We are applying F applied. I am stretching or compressing. I am giving my energy because I feel tired after buat kerja Allah, tarik semua ni. I feel tired. So where does my energy go? It goes and it is being stored in the spring and it is called as elastic potential energy. Alright. Okay, so kita cakap pasal ni juga. So this is the equation for elastic potential energy. 1/2 kx squared. Tapi this is supposed to be final minus initial jugalah sebab dia work done. Work done 1/2 kx squared final minus 1/2 kx squared initial. But when we are talking about elastic potential energy sahaja, then it would be U as 1/2 kx squared. Remember, work done has to be change in energy. Has to be change. Cannot be a single instance punya cerita. Dia kena ada change. Baru jadi work done. But kalau kita nak cakap pasal energy sahaja, boleh. It becomes 1/2 kx squared. So this is your third equation. Now let's do a little recap on what we have learned so far. So kita dah cakap pasal KE, kinetic energy. We also talked about UG, gravitational potential energy. And we also talked about US. Okay, kinetic energy, gravitational potential energy, and elastic force, elastic potential energy. So this guy, KE is equal to 1/2 mv squared. UG is equal to apa? What is UG equal to?
MGH.
MGH. And US is equal to 1 over 2 kx squared. So this is energy, kinetic energy, potential energy. Now, when I talk about work, it has to be change in kinetic energy. When I talk about work, it has to be change in UG. When I talk about work, it has to be change in US. So when I want to find out what is the work done, either positive ke negative ke, it has to be related to the change in kinetic energy. So I can say KE final minus KE initial ataupun 1 over 2 mv squared minus 1 over 2 mu squared. So this is my work done. For this guy, this should be mg. M and g does not change, so I can only change my h. So this is delta h. And then for work done for spring, I cannot change my K. K is related to the property of the spring. So the only thing that I can change is X. So if I want to have this delta over here, I need to put in the delta somewhere else juga. So it becomes 1 over 2 kx final squared minus 1 over 2 kx initial squared. Macam tu. There has to be the change. Okay, so that is your 3 mechanical energy. What else did I miss? Untuk KE, there is a work energy theorem. What does it tell you? Kena hafal Work energy theorem tells you that work is related to the change in kinetic energy. Tapi jangan tulis macam ni, tulis penuh-penuh. Give me what is KE, tell me what is W. You cannot just put W and expect me to know that you know what is W. Sometimes people cakap W tu benda lain, weight. So that is already wrong. So you have to define what is W, what is KE, what is U when you are writing equation. Okay, jangan tulis equation lepas tu biarkan macam tu saja. Sebab kadang-kadang orang tak faham pun equation tu apa. Dia tulis je. Okay, so UG, what else do we know about UG? It is related to position. Yang ni related to velocity. Let me write that somewhere. This is related to change in velocity. Related to change in velocity. Okay, so this is related to change in height. Okay, and this is related to change in deformation. In this sense, deformation means compression or extension. Related to deformation of spring. Okay, so what else? This is related to apa kita dah tahu. So kalau saya nak lukis, I would know that there is some change in height from H1 to H2. I would have work done. Kalau saya cerita pasal ni, I would know that my spring is being extended or compressed. And there is some delta X happening. There is that change. Therefore, I know that there is going to be work done. When I have V that is greater than U or U that is greater than V, I know that there is change in velocity. Therefore, I would know that there is work done. So this is how you determine work done in these situations. What about the graph? The graph for mg, F is, the force for mg is constant kan? So the F is constant over H. Your F does not change. Your U changes. So what about this guy? This is not, tak ada F kat sini. Kita cerita pasal Fx. Yang ni ada F applied. This is also F applied. So this is related to X. You would have a graph like that. So this is the graph associated to the forces acting for UG and also for US. Apa lagi? I think that's it. Okay, so how many minutes do we have left? 15. What do I want to cover in the last 15 minutes? Okay. So based on the conservation of energy, we know that energy cannot be created nor destroyed, right? So if I have a mass that is, if I have a mass that is connected to a spring like this one, so when I when I am stretching this by F applied, bukan. Kejap. This is not a good example to teach. Sekejap MGH. Okay. Cuma sekejap, saya tengah fikir macam mana nak cerita supaya korang tak confused. Okay, so based on the conservation of energy, we know that energy cannot be created or destroyed. So in this case, we know that, we assume that this object has some potential energy that is not going to be created, that is not going to be increasing or decreasing. Dia kena maintain sama. This whole system, they are connected. They are one system. So this system has a spring and also a mass. So a mass is associated with mg force, and the spring is associated with the elastic force of the spring. So one guy is this way. So this is the original state of the spring and also the mass. Waktu ni kita pegang mass tu, kita tak buat apa-apa lagi, kita belum start apa-apa lagi. So saya lepaskan mass tu. So mass tu jatuh ke bawah. Dia tarik the spring. So when the mass extends the spring, what does the spring want to do? What does it want to do? Kita tahu spring ada banyak feeling. So apa perasaan dia waktu ni?
Return to its original state.
Dia nak pergi ke original state. Dia tak suka perubahan. So kita ada mg, it's going down. This is our force mg. Fg equals to mg. We have a force going down. The spring does not like that. What happens? It will try to oppose this change with the same amount of force. We'll try to oppose this change with the same amount of force. So dia akan bagi Fs, where Fs will be equal to Fg. Kena sama sebab dia nak oppose. Dia nak oppose change. So when you have this, when you have Fs acting and there is a change in displacement, there is a change in the spring, it's extending, right? You would have UE, right? You would have UE because it is related to the force, the spring force, the elastic force. And when you are changing in height, you would also have a change in UG. Okay, in this case, you are extending the spring. Let me repeat myself. You are extending the spring by a mass. So you would have 1/2 kx squared. Ada value x kat sini. Ya, ada perubahan kat sini kan. So and then when you are moving from H0 to H1, you are also changing the H. So that means you are going to have UE and UG. Dan UG dan UE akan berubah. Tapi kalau dia orang berubah, macam mana kita nak conserve energy? So if they are changing, how do we conserve the energy? That is the question. Okay. So the answer is one has to go up and the other has to go down. So for example, my mass is going down. Therefore, I am losing gravitational potential energy. Sebab H saya negatif, saya ke bawah. My I'm losing gravitational potential energy. So this guy goes down and this guy is extending, dia punya X membesar. So this guy goes up. So the amount of change, let's say dia naik by 10 Newton, this guy has to go down by 10 Newton supaya semua ni jadi constant. Okay, so what if I am from here? My spring is down here, I'm compressing it. Tapi kita kena buat compressing daripada sini lah. Okay, let's say this is the original state and I am compressing my spring to become and the mass to be over here. So dia compress lah. So delta X dia mengecil, delta X becomes negative, but my H becomes positive, it's going up. So now my UG is going up because I am gaining potential energy. I'm gaining gravitational potential energy. Let's say it increases by 10 Newton and I am losing elastic potential energy by the same amount. So I would have a constant energy in the system. So dia akan jadi macam ni, satu naik, seorang lagi turun. Seorang lagi naik, seorang lagi turun supaya sistem ada constant energy. So this is how they conserve the energy. It changes forms. So this guy loses, it changes to become UE. This guy increases, dia ambil daripada sini, dia naikkan ke dia. So it changes form. But energy ni boleh berubah-ubah. So any questions so far? So I think I'm going to end class at this point. Kita akan belajar conservation of energy in more detail in the next class. So that is going to be related to your lab as well. So that is going to be on Thursday. Thursday, good. Okay, bye guys. Take care. Kalau soalan boleh tanya.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Thank you,
Thank you for
Doctor.
attendance.
Thank you,
Thank
Doctor.
you, Doctor.
Thank you, Doctor.
Thank you, Doctor.